Okay, once we understand basic operations with radicals, simplifying, how we can multiply and divide radicals that have the same index, how we can work with addition and subtraction with radicals, we can then move on and discuss multiplying radical binomials, which is to say expressions that involve a sum or difference of a radical with another number, whether that's another radical or an integer or possibly just some rational number. So I see here's an example, 3 plus 2 square root 5 times 6 minus 3 square root 5. Now, essentially we're going to do this the same way we would if we were multiplying 3x plus 4 and 2x minus 7. We can FOIL this, we can multiply using a little box, we can split it up and distribute. All of those will still work here. You have to be careful. There is one little wrinkle that is going to show up that didn't show up when you did this with things with x's. So I will show this by splitting it up and distributing. So I'm going to multiply 3 by 6 minus 3 square root 5, and I will also multiply positive 2 square root 5 by 6 minus 3 square root 5. Now when you do this, you have to be very careful. Some of this is quite simple. 3 times 6 is 18. 3 times 3 square root 5, well, 3 can be multiplied with the 3, and that's 9. And then I will still have the square root of 5. What about down here? I'm still going to distribute 2 square root 5 times 6. Well, I will multiply the 2 and the 6. I will multiply those like parts, if you will. So that's 12 square root 5. And then, what happens down here? When I go to multiply 2 square root 5 by 3 square root 5, well, I'm going to multiply the like parts together. 2 times 3 is 6. And what is the square root of 5 times the square root of 5? Now, if you understand the way we work with radicals, you know that the square root of 5 times the square root of 5 is the square root of 5 times 5, or 25, which is 5. But if you're thinking in terms of the actual mathematical definition of a square root, by definition, the square root of a, for some number a, is a number where if I multiply it with itself, what I get is whatever's in that radicand. I get a. By definition, that's what a square root is. So the square root of 5 times the square root of 5 will be 5. The square root of 10 times the square root of 10 is 10. The square root of 29 times the square root of 29 is 29. All right. So now I'm going to look to simplify this. So I see 18 minus 9 square root 5 plus 12 square root 5. First thing I'm going to simplify is this 6 times 5. That's 30. And now what I want to look to do, whoops, I forgot to write my subtraction sign. And now what I want to look to do is combine the like terms. Well, the integers are like. 18 minus 30 is negative 12. And these are both square root 5 terms. They are like. Negative 9 square root 5 plus 12 square root 5. I combine based on these numbers outside. Negative 9 plus 12 is plus 3. And that's essentially it. These problems get a little bit more complicated, mainly by giving you radicals that you need to simplify somewhere along the way. But this is in essence how you do this. There's not a whole lot to it. This right here, this part of multiplying 2 square root 5 with 3 square root 5 is the trickiest part. Let's look at a couple more examples. Here I have 5 plus 3 square root of 11 times 2 plus the square root of 11. And again, you can FOIL or do whatever makes the most sense to you. Just be careful. So if I do this, I get 10 plus 5 square root of 11. Down here, I will have 6 square root of 11. I will have plus 3 gets multiplied with the 1 that we understand is in front of that radical. Square root of 11 times square root of 11 is 11. And then I'll look to simplify. Well, I know that this is 33. So I have 10 plus 33, which is 43, plus 5 square root of 11 plus 6 square root of 11 is 11 square root of 11. And I cannot combine this any further because realize in both of these I got an integer and something multiplied with a radical. These are not like terms because this doesn't even have a square root attached to it. Please note this doesn't say negative 12 plus 3. This doesn't say 43 plus 11. It says negative 12 plus 3 square root 5. This is its own thing, just as down here 11 square root of 11 is its own number. In example 3 right here, this is a bit more complicated. One, because it introduces an error that some people will make. Recall, if you are squaring something, that means you are multiplying it by itself. So we notice that first. The other thing you can notice here is you might, as you think about it, the square root of 8, that can actually be simplified. I could simplify it now. I could simplify it later. I'll save it until later. So if I do this, square root of 8 will be multiplied by square root of 8 minus square root of 3. Minus the square root of 3 will be multiplied by the square root of 8 minus the square root of 3. So when I multiply these, the square root of 8 times the square root of 8 is 8. The square root of 8 times 3 is the square root of 24. Over here, the square root of 3 times the square root of 8 is the square root of 24. And the square root of 3 times the square root of 3, notice these are both negative, so I'll have plus 3. So then what do I have? I have 8 plus 3, which is 11, minus 2 square roots of 24. So this can happen sometimes. You should check at the end to make sure your answer is fully simplified. Square root of 24 is not fully simplified. In this case, it's because we had the square root of 8 in the beginning, which could have been simplified. Some problems you might get a square root that can simplify by the end, but not have had one in the beginning. Either way, let's just double check. 24 is, among other things, 4 times 6. And you can break that down into primes if you feel you need to, but since there's a 4 under this square root, I know that means I can pull a 2 out. That 2 will come out and be multiplied with the 2 that is already there. And what I will get for my final answer is 11 minus 4 square root 6. Okay. Now, discussing this topic, there's also something that comes along with it. We discussed this in polynomials, and we really saw it when we talked about quadratic formula first. If I have an expression involving some type of radical, a plus the square root of b, its conjugate means I take this expression, and what I'm going to do is just change the operation between the rational and irrational parts. So a plus the square root of b would have as its conjugate a minus the square root of b. 4 minus the square root of 3 has as its conjugate 4 plus the square root of 3. Negative 5 plus 2 square root 15, a bit more complicated, but to get its conjugate, what do I need to do? I'm just going to change the operation. So I will have negative 5 minus 2 square root 15. Why is this important? Well, it's used in a couple ways. I will show you an application if you do wish to go beyond this. We know from our study of factoring that a squared minus b squared, this is a difference of squares, is equal to a plus b times a minus b. If I apply that thinking to the product of two conjugates, then what I should get here is 5 squared minus the square root of 6 squared. If you can catch on to this and latch on and use it, this does save you some trouble, at least when this comes up. What do we get then? We now have 25 minus 6, or 19. Don't be afraid to do all the work. I will do another example right here where I show it in full detail. I don't just use this short relationship. I want to see here how this turns out. So I can see these are conjugates. Based on the different signs, these are in fact conjugates. I have one subtraction, one addition, and all the numbers are the same apart from that. So, I'm expecting to get as my answer 8 squared minus 5 square root 3 squared. That's what I'm expecting to get. Now again, you can FOIL it, you can split it up and distribute, you can use a box if that's what makes the most sense to you. Just be careful. Five square root 3 times 5 square root 3 will be 25 times 3. And you notice what has happened here. On this side I have plus 40 square root 3. On this side I have minus 40 square root 3. So those do combine to be 0. So what am I left with? I'm left with 64 minus 75, which is negative 11. And in fact, that is what I would have had up here. 8 squared is 64. If I square 5 square root 3, I will have 25 times 3. So that does give me the same work. Knowing these conjugates is useful. If you continue on your studies in math, you will definitely encounter this. This comes up in pre-calc, for instance. And I'm going to show you that little extension right now. As of the time I'm making this in February of 2021, this is not on your test, but it is something that I think is worth knowing. So previously we talked about rationalizing a denominator, which is to say trying to get radicals out of the denominator. There are some very simple examples with that. Here I have this lonely square root of 6 in the denominator. To get it out, I multiply the square root of 6 into both the numerator and the denominator. What does that give me? Well, I have 15 times the square root of 6 over 2 times 6, or 15 over 12, 15 square root 6 over 12. And I look to simplify these numbers that are outside. Well, 15 over 12, that simplifies to 5/4. That's the simple example. In some cases, I might have something more complicated. Like here I have 21 over 3 plus the square root of 2. I can't just multiply by the square root of 2 here. It won't actually eliminate the radical because I'll have to multiply 3 by the square root of 2, and I'll basically be right where I am right now. So what I can do instead is multiply by the conjugate of this expression. Why is this useful? Again, what happens when I multiply by the conjugate? Well, up top, I can just distribute, but down here, this is essentially a difference of squares is what I'm multiplying. This product is going to be 9, or 3 squared, minus the square root of 2 squared. Let me write that to make it a little bit clearer. That's 9 minus 2, that's 7. So what do I have? I have 21 times 3 is 63, minus 21 square root 2, that's what's on top, and that's over 7. And then I would look to simplify this. All three of those numbers are divisible by 7, and I'm left with 9 minus 3 square root 2. That also shows us a little look into why we might want to rationalize the denominator. This looks very gross right here. It looks much more straightforward after I have rationalized. I'm going to do one more example like that just so you can see how this works if you're trying to master this skill, which, like I said, as of me making this in 2021, this is not on our test. I see down here I have 8 minus 3 square root 5. I multiply by the conjugate, 8 plus 3 square root 5. What does that give me? Downstairs I have 8 squared minus 3 times the square root of 5 squared, or 64 minus 9 times 5, which is 64 minus 45, or 19. What do I have up on top? Well, 12 times 8 is 96 plus 36 square root 5. All this is over 19. So I can't simplify that. 19 doesn't go into this. This will just be my answer. So again, it's just a little glimpse into why the conjugate is considered to be important. And of course, there are harder variations of this problem. Up top, I could have something more like the denominator, like if the numerator was 4 plus the square root of 7 or something like that, or just the square root of 5. That could give me a more interesting problem. There's a problem here for you to try, and there's some additional practice problems on this sheet if you would like to try those.